Okay, so we're going to change gears a little bit here. We're going to return to limits. In particular, we're going to show you some techniques. Or I'm going to show you some techniques on how to deal with certain kinds of limits. And these limits are actually called indeterminate forms. And the technique is basically what is called L'Hopital's rules, French guy. So seems kind of odd that we're returning back to limits, but you'll see why. So this is, like I said, going to show you some additional techniques on how to evaluate some specific types of limits, and the reason we're doing it now is because you'll need it for the next section and some of the sections thereafter. So let's just take a look at this, right? Again, go through the the standard deal here, right? Obviously direct sub doesn't work. There's no manipulation of algebraic, there's no identity. You kind of get stuck pretty quick, so the only way would be to approximate, which we don't want to do. So notice that not only does the bottom tend towards 0, but actually the top tends towards 0 as well. Now, this 0 over 0, we don't want to write this, right, because it's nonsense. You can't put 0 in the denominator. But when both the top and the bottom are getting small, as in this case, this is what's actually called an indeterminate form. Okay, so if you have a limit of the form f of x over g of x, where both f and g are going to 0. Now the limit then may or may not exist, and it's called an indeterminate form of type 0 over 0. Now, why do I say it might or might not exist, right? There's some thought that needs to go into this for a second. Like most people would say, well, why wouldn't it be 1, right? If the top's getting small and the bottom's getting small, shouldn't it just be 1? Well, possibly, but not always. Why do I say that? Well, it depends on how fast the top and bottom are getting small, right? So think about this. If the top is getting smaller a lot faster than the bottom, then the limit is probably going to go to what? It's going to get smaller. It's going to go to 0. If the bottom is getting smaller a lot faster than the top, then that's going to go to infinity. Actually, that limit will not exist. If they are going to 0 at the same rate, then it will be 1. Now wait a minute, I said at the same rate. What do we think of when we think of rate? The derivative. So now you'll see when we get into this technique, it shouldn't be a surprise. So in this case, both the top and the bottom are heading towards 0, but you can still do this, right? Direct sub obviously won't work, but you can cancel like it says here, and then you can use direct sub. That's okay. We did a very long geometric argument for this last semester, and we found out that that limit is actually 1. Again, you know that, but that's from a geometric argument. But those methods don't work on this. So what's this technique? Well, it's basically L'Hopital's rule. Well, what does the rule or the technique say to do? Well, if you have the situation where they're both getting small, top and bottom are both going to 0, or, right, or another option, you can use the same rule. If the top and bottom are both going to plus or minus infinity, the plus or minus doesn't matter. Okay, they're either getting large and negative or large and positive. You have indeterminate form of type 0 over 0 or plus or minus infinity over plus or minus infinity. So how do you do that? This is the technique, right? You take the limit and you rewrite it as the limit as x goes to a. You take the derivative of the top and you divide that by the derivative of the bottom. Okay, why the derivative? Well, because the derivative is rate, right? Rate. If we're trying to find out which one goes faster, which rate is greater, okay? Provided this exists. Notice that you're not using the quotient rule on this. You're just doing the derivative of the top and dividing by the derivative of the bottom. So let's see how this works. Again, you can write this, and I'm indicating, I put a little, which I want you to do as well, I put a little LH over the equal sign. What does that tell me? That tells me you're applying L'Hopital's rule. Okay, so what does it say? It says it's the limit as x goes to 1 of the derivative of the top, which is what? Well, the derivative of the ln of x is 1 over x, and the derivative of x minus 1 is simply 1. Now, once you get here, what happens as x goes to 1? Well, we have 1 over 1 over 1, so this limit exists and is 1. Okay, so it looks like they're going at the same rate. Okay, and like I said before, you don't use the quotient rule with L'Hopital's. Let's take a look at this particular limit, right? What happens to the top? As x gets very large, the top gets very large. As x gets very large, the bottom does as well. So this is a candidate for L'Hopital's. It is an indeterminate form. So you'd put the little LH above, and you'd take the derivative of the top, which is e to the x, and the derivative of the bottom, which is 2x, and guess what? Top still gets big, bottom still gets big. So are we stuck? No. Still in indeterminate form, so you can apply L'Hopital's again. Notice that I've indicated that with the LH. The derivative of the top is still e to the x. The derivative of the bottom is now 2. This is not an indeterminate form anymore. The top gets big. Big number divided by 2 is still a big number, so this limit does not exist. Okay, and you probably knew that before we started. The top is exponentials grow much larger than power functions. Okay, the top one. How about this one? What happens as x approaches pi from the left, right? Well, the top goes to 0. Be careful. The bottom actually goes to -1 from the left. So it's 1 minus -1. So you get a 2 in the bottom. So this is not an indeterminate form. Okay, this is actually 0. The lesson being here, just because you're going to like L'Hopital's, it's pretty easy. Don't just launch right into it. Okay, make sure that you have an if you don't have an indeterminate form, you cannot use the rule. Right, doesn't apply here. So the rest of this section, which I'll break up into 2 parts, is essentially going to be other types of indeterminate forms and what to do with them. Okay. So the first type and the main type, like we said, is 0 over 0 or plus or minus infinity over plus or minus infinity. So let's take a look at another type. Okay. Let's say the limit as x goes to a of f is 0. And the limit as x goes to a of g is plus or minus infinity. What happens when you multiply them? Okay, this is actually an indeterminate form of type 0 times infinity. Begs the question, why is that not 0? Well, again, this is heading to 0, and this is getting large, either large and negative or large and positive. So there's a struggle or a battle going on here. It depends on which one is going there faster. If f is getting smaller a lot faster than g is getting larger, it will be 0. But if g is getting larger way faster than f is getting smaller, it will not be 0. So that's why it's an indeterminate form. We're unable to determine what's going on here. Okay. So how do you do this? Well, actually, this is easy. You just do an algebraic rewrite. So f times g is the same as f divided by 1 over g is the same as g divided by 1 over f. Agreed? That's just basic algebra. So why would we do that? Well, if f is going to 0 and g is going to infinity, what happens here? Well, f is still going to 0, and if g goes to plus or minus infinity, 1 over plus or minus infinity is 0. So this is a 0 over 0 type. Turns it into a 0 over 0. Likewise, if f goes small and g gets big, what happens here? Well, I have big over 1 over small, which is big over big, so this is actually the other type. So you're just turning it into what we already discussed. Okay, that's all that's necessary. So this one's pretty easy to deal with. So it turns it into the type that we've already dealt with. So let's take a look at this. As x approaches 0 from the right, this gets closer to 0, of course. And as we approach 0 from the right, what happens to the graph of the ln? Right, it goes like this. So as we approach 0 from the right, this goes to negative infinity. So this is an indeterminate form. 0 times infinity. Which means we have to flip one of the functions. Now you have to be careful because it does matter sometimes which one you flip. So if you were to write this as x over 1 over ln of x, is this something that's easy to differentiate? No. You'd have to use quotient or bring it upstairs to the -1 and use chain. It's a pain in the neck. Is this easy to differentiate? Yes. So I would start with this one first, which I believe is what I did here. In fact, I think it turns out the other one doesn't work. So we have a 0 times infinity or 0 times negative infinity type. So we flip one. I've flipped the x. So now this gets large and negative, and this gets large and positive. So this is type infinity over infinity. I can now apply L'Hopital's. That's what the LH is there for. The derivative of the top is 1 over x. The derivative of the bottom is -1 over x squared. Now, before you get going with this, if you just evaluate this as is, you will get another indeterminate form. But before you do that, 1 over x divided by this is the same as this, which is just the same as this, right? This simplifies quite a bit. And then you can use direct sub, so you're done. So this limit was 0, so clearly this was getting, you know, this one. This was getting smaller faster than the ln of x was getting large and negative. Okay. So like I said, I'm going to break this up. There's a couple other types, but it's a lot of information at once, so it's a good time to maybe break this up into 2 parts. This will be the first part of section. Actually, that should be section 2. Sorry, I'll fix that. And then we'll discuss some other types. So these will all be of the type 0 over 0, infinity over infinity, or infinity times 0. Okay, and then we'll move on to the other parts in the next video.